for my nursing.
Good afternoon. Welcome to the last circuits class before spring break. A few announcements before we start in with the probably want to mute yourself. Before we start with the last third of the third of lecture 6. I realized that I made the due date of homework 3 during the spring break. You know, I don't like that. I don't want to do that to you guys. So I will extend. So good news, bad news. The good news is that I'm going to extend the due date for homework 3. That's the good news. The bad news, I'm going to extend it to, let's see, to the 7th of April. I'm not going to change the PDF. I'm just going to make the due date different in Blackboard. I still want you guys to have practice with op amps before the midterm, because the midterm will have op amps. And so there will be an assignment, a 4th homework set that will become available before homework 3 is due, because I want you guys to have a week to work on some op amp problems. It doesn't necessarily mean that the homework number 4 will be due before the midterm, but at least you'll have the opportunity. Someone's already had enough. I think it's the fastest exit so far. You don't need to actually submit the 4th homework, but I want you at least to have the opportunity to practice op amp questions if you want before the midterm. So again, the midterm is on April 12th during class. Bring your webcam, your brain, and a pencil. I don't think you'll need a calculator. Let's see. Okay, so we only have about 11 slides to cover today, but those 11 slides are pretty heavy. And so initially thought I was going to be a short class, but I'm not so sure anymore, because the content here will require some thinking. All right, so we're going to be solving circuits that have inductors in them. And we're going to be given some initial conditions, and you'll have to use the circuit laws, the law, the fundamental law that governs an inductor is, maybe I'll go back to remind you. This is the fundamental law that governs the voltage across an inductor as a function of the current. So when you wrap the wire in a cylindrical coil and stick something that's ferrous in there, and if you change the flow of current, then that change of current induces a voltage transiently, right? So the voltage across an inductor is a transient phenomenon. If you want to keep the voltage, if you want to sustain the voltage, you have to sustain the change. So for example, if I is a sinusoid, then V will be a cosine. If I is a step function, then well, I'll let you think about. If I is a step function, then V will be very transient voltage, right? It will only be present during that step, during the transition. Alrighty, we did this. This was easy. Did this. And now we are actually presented with a circuit, and we're told the following. We're told that the initial current I that flows into the circuit has this form. It's equal to 4 times 2 minus e to the minus 10t. Right? So first of all, what does this waveform look like? What is the value of the current I at time 0 and at time equals to infinity? Yeah, sorry, 4. 4 is correct. Yeah, you guys both got it. So time equals 0, it is equal to 4. What about a time equals to infinity? Yes. Yes, correct. Right, so we know that it starts at 4 and goes to 8. So it's gonna have this like I don't know if you guys know this term, sigmoidal shape. So it starts off at 4 and then it rises and plateaus at 8. And so the question is, what happens to these other circuit variables, I1, I2, V1, and V2, as that current I is rising from 4 milliamps to 8 milliamps? Okay, so we're also told that and this is very helpful, we're told that the initial current across the 12 Henry inductor is equal to minus 1 milliamps. And so we are asked to find the initial current I1. So we're given the current at all time over here. We're given the current at time 0 over here. And our first question is to define the initial current through the 4 Henry inductor. So remember what I said, KCL holds at all time. KVL holds at all time. And so let's focus on KCL at this node where my cursor is at time 0. I want to write the KCL equation at this node at time 0. Yes, exactly. And so more precisely, you'll want something like undo this autocorrect. More precisely, you have the I at time 0 is equal to I1 at time 0 plus I2 at time 0. So what is the value of a lot of sound effects today? You gotta just keep it clean, all right? This is a family course. What is the value of I at time 0? Oh, you're answering I1. You've already, yeah. So Christian, you're actually answering I1. So I was just asking for I times 0, which we already, oh, we have let me just write this and I'll get to your question. Right, we know that I0 is equal to 4. Right, yeah. Right, and so what is I1 at time 0 then? If I0 is 4 and I2 0 is -1. What is I1, right? Christian, you already answered it, so I'll just say the answer is 5 milliamps. Okay, so we had a student raise their hand, so go ahead with your question. No question. I guess you lowered your hand. Okay. Let us continue. So that part was pretty straightforward, right? We just applied KCL at time 0 at this node here. And we figured out that the initial value of I1 was 5 milliamps. So at time 0, there's 5 milliamps flowing down here. There's a milliamp flowing up here. So there's 4 here, 5 here, and 1 here. Okay. What about the value of VT? How do I solve for this voltage here? Any ideas? What do I have to do to this circuit before I can attempt to solve for V of T?
You could simplify the circuit, like combine all the inductors.
Yes, exactly. So how do I combine it? So I can combine those 3 into a single one. Excuse me. So if I combine, so which inductors are in parallel and which inductors are in series?
The 4 and the 12 are in series. I mean, in parallel.
That's right. And so what are they, what 4 in parallel with the 12 gives you what?
I think I got 4.
It's always going to be less than the smaller of the two numbers.
Okay.
So 4,
3.
yeah, 3, right? Yeah. So, and then that 3 is in series with the 4 up at top. So what's my equivalent inductance for the circuit? Yes, thank you, Kimberly. 7. 7 is the equivalent inductance. Okay. So that gives us the overall inductance. So we have the overall inductance and we have the overall current. So now how do we get the voltage V? Yes, very good. So who can help me with evaluating L times di over dt? So we have to multiply the 7. So one way is just to multiply the 7 by the 4, or yeah, that gives us 28. And then we have to differentiate what's in the parentheses here, right? And so what's in the parentheses, right? Yeah, that looks right. 7 times 40 to the minus, that's correct. There's a minus sign, that's the, no, the minus sign cancels out actually. There's 2 minus signs, right? So 7 times the derivative of this, which is 8 minus 4e to the minus t. And then we apply the chain rule, right? Derivative of a constant is 0. We have minus 4 e to the minus 10t times e to the times minus 10. So this is now our final expression for the voltage across these two terminals as a function of time. So it's 280 e to the minus 10t. Right, so what does that voltage start out? So what is the value of that voltage at time 0? And what is the voltage at time equals to infinity?
So the voltage will be 280 at t equals 0 and
Yeah.
0 at time infinity.
That is correct, right? So it starts off high and ends up low. It ends up at 0. So which is kind of, so that notice that the current started out at 4 and ended up at 8, right? And the voltage starts out at 280 and goes to 0. So different dynamics for the voltage and the current here. Okay, so now we have a solution for I10. We have a solution for VT. How about the solution for V1T? How do I solve for V1 of T, this voltage? Yes, excellent. It's that same derivative, but now multiplied by 4 instead of 7. So divide this by 7 and multiply it by 4, and you get 160 times e to the minus 10t. Yeah, and that's a good question, Christian. So let me so the reason we need to simplify it is if you have an inductor that has a voltage and it has a current, then we know that VL is equal to L times I prime. Okay. And so this is the voltage between this terminal and this terminal. So you have to think about what is the inductance between this terminal and this terminal. Well, the inductance between this terminal consists of this inductor, and this inductor. And so to apply this equation to this circuit, you need to first redraw it in this canonical form. And so that is why you need to simplify the inductors, because otherwise you're not solving for the voltage between this terminal and this terminal. Because between these two terminals, you have a bank of inductors and not just a single one. Hopefully that makes sense. All right, so now we've solved, okay, good. No problem. So we have 280 times e to the minus 10t for V, and we have 160 times e to the minus 10t for V1, right? And so now we can just use KVL to solve for V2, right? We need an expression for V2t. And the way we just apply KVL around this loop here. So in other words, we have another way of doing this is negative V plus V1 plus V2 is equal to 0. And we have a solution for V. That's, where is it? That's here. We have a solution for V1, that's here. And so the remainder is 120 times e to the minus 10t. So now we have this solved, this solved, this solved, and this solved. And we need a solution for I1 of t and I2 of t. So now the question is, I have, for an inductor, I have the voltage, I have the inductance. How do I get the current? Any ideas? Integrate, let's see. I'm gonna go back to the slideshow. Yeah. So, like you said, to go from the voltage to the current, we need to integrate and divide by the inductance. So V2 of t, we know that V2 of t has this form. So we need to integrate that waveform and divide it by the L. And there's one little pesky thing here is that this current I1 has an initial condition which is non-zero. Namely, the initial condition is 5 milliamps. So when you integrate, you have to remember to include that as your integration constant. And that's why you get the 5 milliamps here is just the initial current to add this inductor at time 0. So when we're beginning the integration, this inductor already has a current of 5. So anything that happens between 0 and t has to get tacked onto that initial value. And so fortunately, integrating an exponential is easy, right? It's just the integral divided by the negative 10t. It's just the exponential divided by the negative 10t. And so we have 30 divided by negative 10 gives you negative 3. Evaluate that at time t and 0. And this gives you, it's interesting, you get an answer that is a combination of a constant of 8 minus 3 times e to the minus 10t. So now let me ask you, for I1, which is the current through the 4 Henry inductor, what is the value at time equals 0, and what is the value at time equals to infinity?
At time equals 0, it's 5 milliamps.
That's right.
And then at time equals infinity, it's 8.
Exactly. So it starts off at 5 and it ends up at 8. And notice that this current starts off at 4 and ends up at 8. So what does that mean about this current at time equals to infinity? This one ends up at 8, and this one ends up at 8. So what does this one have to end up as?
0.
0, exactly. So that's like a good sanity check. When you do the same integration for I of 2, right? So we know that V2t is 120 times e to the minus 10t. So the only difference between the integration to solve for I1 and the integration to solve for I2 is the value of the inductance and the initial condition.
What did you do?
I was walking and it's bleeding. You're having more baby.
Say
Take a shower,
hi.
wash.
Say hi to YouTube.
I'm just gonna wash my leg because I took a shower last night.
Okay.
So the integration. So the
Hey.
sub. So our inductance is equal to 12, and our initial current is equal to -1. It's all good. It happens over the span of a 28-week course. Anyhow, this integration is just like this one, except that we have a different value of the inductance, and the initial current is -1. So when you evaluate it, you get, as you would expect, a term that goes to 0 as t goes to infinity. Namely, you get a current here of -e to the power of -10t. All right, so I'm gonna pause it here. I know that this question has, I think, confused some in the past. So if you guys have any questions, please let me know now. Okay. I'll take your silence as 100%. Oh, what is the V2 representing? Yeah, so the V2 is just a, so these two inductors are in parallel. So it's just a voltage across those two inductors. They are constrained to have the same voltage at all times because they're connected. So it's just if you take two inductors and you hook them up to the same terminals, they're gonna have different currents, but they're gonna always have the same voltage. All right. Let's do this one. Hopefully I can get a lot of help from you guys. So we have I1 of t. So we're given an expression for this current here. And we're also told that the initial value of I is 1.4 amps. And we're asked to find a whole bunch of quantities over here. So let's start off with the easy one. How can we solve for the initial value of I2? So the initial value of the current flowing through the 3 Henry inductor. Any ideas? What's the initial value of I1? People are dropping like flies. You guys all headed to Miami Beach? No. What, Fort Lauderdale? 0.6. Thank you, Christian, for keeping me on task. All good. Yeah, the initial value of I1 is 0.6. The initial value of I is 1.4. So what is the initial value of I2? Audience says 0.2. I think it's 0.8 because it's the difference between 1.4 and 0.6. So the initial value of I2 is 0.8. So now, see, I think I may have gone out of order when I did this question. Oh, maybe not. Oh yes, I did go out of order. I don't like the order of these. I like to first solve for V1 before I solve for I2. So I'm gonna say, let's get an expression for V1. So V1 is the voltage across these two inductors. And so I have an expression for the current through I1. How do I translate that into a voltage? How do I go from current to voltage in an inductor, across an inductor? Integrate. Are you sure? Yeah, so Christian, that would be the voltage. So almost. So what's the voltage across an, yeah, differentiate, thank you. Differentiate. So we have to differentiate, let's say, I have 1. And you could, if you had an expression for I of 2, you could have used that equally, but we're going to use I of 1. So the derivative of this is negative 1.2 times 6. Sorry, the derivative is negative 1.2 times e to the minus 2t. And that gets multiplied by the L, right? Because the voltage across an inductor is equal to L times di over dt. So we now have an expression for V1 of t, which is great. And let's see, what else can that give us? Where would I go next with this? I would probably, I think the next thing I did was get I2 of t, yeah. So now I'm just gonna show it. I2 of t, so this inductor here is sitting at V1 volts. And so if I integrate, now is when you integrate the voltage to get the current. And so the integral of V1 from 0 to t divided by the inductance plus the initial condition gives you I2 of t. So let's integrate this expression. So let's put this into the integrand and evaluate. Okay, and so the integral, the constant will come out in front of the integral. Then you get a division by -2. Add your integration limits, which here are just t and 0. And this, the 0.8 here, corresponds to our initial condition. We said that initially, the current I2 is equal to 0.8. And so you do all this arithmetic, and you get a value of negative 0.4 plus 1.2 times e to the minus 2t. All right, so this current starts out at a value of 0.8 and ends up at a value of negative 0.4. So it's starting positive and going to negative. Okay, so now I have an expression for I of 2. How do I get an expression for I of t now? How do I get the equation for I of t?
Will you add I1 and I2?
Exactly. You would via KCL, like was said on the chat, you would add I1 and I2. So it gives you negative 0.4 plus 1.8 e to the minus 2t. So now we have I20, we have I2t, we have IT, we have V1 of t. We're still missing V of t and V2 of t. Right, so we're still missing 2 more quantities. But now, remember what I said last time is that we needed to convert those inductors into a single inductor to relate V to I. So we can do the same thing here. So what is the equivalent inductance of this circuit? Ten is correct. Excellent. right? Because 3 is in parallel with 6, which gives you 2. And then 2 plus 8 is equal to 10. Right, so the total inductance is 10. So we know that V is equal to 10 times the derivative of I of t. Right, so 10 times the derivative of this. And when you evaluate that, you get negative 36 times e to the minus 2t. So now I have V of t, and I also have V1 of t. How do I use those two voltages to get the third? KVL, exactly. So how do I apply KVL? Which two, what is going to be the expression for V2 of t? So I can write negative V of t. Yes, exactly. V of t minus V1 of t. That's excellent. Right? Because if I wanted to write the, if I wanted, yeah, here it is. I didn't even need to, yeah. Right, so the overall V, the voltage rise from here to here, has to equal to the voltage drop from here to here, plus the voltage drop from here back to here. So we just have to subtract V of t minus V1 of t. And what you get at the end is that voltage 2 is given by negative 28.8 e to the minus 2t. Notice one thing, that all of these circuit quantities here have the same time constant of 2. That's an important thing. All of these voltages and currents, they increase or decrease at the same exponential rate. All right. I'm going to take a minute here, take a sip of water. Okay. Moving on to a few applications. So this is where we combine op amps with capacitors. It is generally not being the favorite part of the course for students, but it's not too bad. You just have to do some KCL to understand it. Excuse me. One thing to note, a practical consideration is that resistors and capacitors can be made very small and printed, on circuit boards. That's not really true for inductors. And so here we're going to consider just combining resistors with capacitors and op amps. We're not going to consider op amps with inductors. But that's not to say that inductors are useless. They're very, as I've alluded to, they're fine application. I believe that every doorbell has an inductor, for example. Loudspeakers, power supply. So inductors are useful. They can't be miniaturized in the same way that resistors and capacitors. Okay, so why are capacitors and inductors special? Well, for one thing, they're capable of storing energy, which means that you can charge them up and then have that energy released back to a part of the circuit when needed. That's a useful property. So they act as stores of energy that can be retrieved at a later time. They also are good at opposing abrupt changes in either voltage, in the case of a capacitor, or current, in the case of an inductor. So like you may have heard the term surge protection. So these are elements that basically prevent a device from receiving, an instantaneous change in voltage, which could damage the circuitry. And so capacitors and inductors, the fact that they oppose abrupt changes in voltage or current find practical use. And the last one is really important for telecommunications. Now, namely, what you will see later on in the course in more detail is that they have an inherent frequency sensitivity. So remember I said that, for example, just take the case of a capacitor. We know that its current is proportional to the derivative of the voltage. And so if you make the voltage across the capacitor a sine, then its voltage will be a cosine. And for a sinusoid, the rate of change is intimately related to the frequency. So a high frequency sinusoid is just a sinusoid with a higher derivative than a low frequency sinusoid. And so that property means that capacitors and inductors respond differently because they are change detectors, and because frequency is really a measure of change with respect to time. Capacitors and inductors are inherently sensitive to the frequency of your current and voltages. So we're going to consider putting capacitors into an op-amp, and we will see that the resulting element will allow you to either integrate or differentiate voltages. All right. So here is an example of a circuit. So remember I said at the beginning of the op-amp lecture 5 that an op-amp is a versatile element. It can compute different types of operations on voltages. And one of those operations is the integral. And so this is an inverter, as we saw before. So this op-amp with a resistor on the inverting input and a second resistor on the feedback path will take VI, and it will multiply it by a negative gain at the output. Now, if you replace the feedback resistor with a capacitor, what you will see on the next slide is that will produce an integrator. In other words, the output here is going to be directly proportional to the integral of VI, which is useful if you're interested in, summing a voltage across time, for example. So if you want part of your circuit to have memory, to remember, the history of a voltage, this is one way of doing that. And so let's do KCL at this node here, at node A. We know that IR has to equal to IC, right? Because no current can travel into the op-amp, because the ideal op-amp assumption. Do we have an integrator in our lab? Well, you can build this device, right? You have an op-amp, you have a resistor, and you have a capacitor. So you'll be able to build this if you so shall choose. So the op amp is like a little, it's like a black, how do I explain it? No, yeah, it's a good question. Yeah, so you plug this in and you plug this in, but the op amp itself comes as a single element. Alrighty. So we know that IR has to equal to IC, and IR is equal to VI over R. And IC is going, as you'll see, is going to be equal to C times the derivative of V naught with a minus sign. All right. Yeah, caterpillar, that's right. I was gonna say centipede with 8 legs, but that just sounded stupid. All right. IR is VI over R, right? Because of Ohm's law. And then notice that this node here, node A, is sitting at 0 because the other op amp input is also at 0. And so this is 0 volts and this is V naught. So the voltage from here to here is 0 minus V naught. So it's minus V naught across the capacitor. And that's why you get that IC is equal to negative C times the derivative of the output voltage. And so we equate these two, and you do a little bit of manipulation. You get that dV naught is equal to negative 1 over RC times VI dt. And now you can integrate both sides of the equation from 0 up to time t. And what you get is that the output voltage at any time t is equal to the integral of the input voltage divided by negative 1 over RC. So this is the first time that we see our RC time constant. You've probably heard of this. So the product of R and C are going to define the time course of your integrator. And so if you assume, for example, that your output starts off at 0, then all you have is that V naught is equal to negative 1 over RC times the integral of the input. So the output is equal to the integral of the input divided by RC with a minus sign. So this is the definition of an integrator. You know what R and C are. So if you want to know the value of your integral without this constant, you can compensate for it. Okay, so the output of voltage of the integrator is proportional to the integral of the input voltage, right? So you plug in some voltage, and what comes out on the other end is the integral of that voltage. So this is the output is now a time varying quantity. So generally we will also have a resistor over here. We don't include that here because it makes the analysis of this circuit a little bit more involved, but the principle is the same. That if you put your capacitor on the feedback loop, you end up integrating the input voltage. And the other thing about this that you have to pay attention to is that this integral should not exceed your power supply voltage, because otherwise you'll be asking your op amp to produce a voltage that it cannot physically generate. And so you have to make sure that you do not saturate the op amp. So don't ask it to, if your power supply is, I don't know, plus or minus 5 volts, you can't ask it to produce an output of 20 volts, for example. Alrighty. So let's actually do an example of an integrator. So we have two inputs, V1 and V2. V1 is connected with a resistance of 3 milliohms, and V2 is connected with a resistance of 100 kiloohms. It will just saturate. So if you ask it to produce higher than what it can, like for a power supply of, let's say, plus and minus 5 volts, the highest voltage that it can produce relative to ground is 10 volts, for example. So it will just always saturate at 10, no matter what the correct answer should be. It doesn't break. It just clips. So I don't know if you've ever looked at a music waveform, like an audio waveform, where the signal is clipped. So like it's hitting the ceiling. That's basically what the op amp would be doing. Okay, let's apply superposition to this circuit. So the output voltage is going to be equal to it's going to have two parts. It's going to have the output voltage here is going to consist of the response to V1 plus the response to V2. So the response to V1, we know from the previous slide, is going to be equal to the integral of 10 cos 2t divided by R1 times C with a minus sign. The response to V2 is going to be the integral of 0.5 t divided by R2C. So notice that the integral of this is going to be a sinusoid, and the integral of this is going to be a quadratic. So let's actually do the math. We have an integral. So these are our RC constants here. So R is either equal to 3 megaohms or 100 kiloohms. Our capacitance is equal to 2 microfarads. So 2 times 10 to the minus 6. And then the integral of a cos is a sine. Right? And we have, using the chain rule, we have to divide by 2. And the integral of 0.5 t is equal to 0.5 t squared over 2. So when you evaluate those terms, you get a resulting output of negative 5.6 sine 2t minus 5.25 t squared, all in millivolts. So you get a summation of a sinusoid, which is bounded between negative 0.833 and positive 0.833, and a quadratic term. Now this quadratic term, again, you have to be careful here because this t squared will get larger and larger. And so here's an example where you would have to limit the temporal extent of this waveform. Otherwise, they would totally saturate the amp. Because this quadratic here is going to grow higher and higher, and it will produce negative saturation. Alrighty. Another example here. Yeah, saturating the amp is bad because essentially the op amp is performing a numerical computation. And so your device, let's say the output of your op amp is controlling, I don't know, make something out. It's controlling a robotic arm. So, or controlling a motor, for example, right? And so the way a DC motor works is that the speed of your motor is proportional to your voltage. So if the op amp saturates, then the motor will not be moving at the required speed, for example. And so it is very bad. You want to avoid saturation because the rest of your circuit will not operate as intended. All right. So here we have another integrator circuit. We have a resistance of 25 kilo ohms, a capacitance of 10 microfarads, and we are asked to determine the output voltage when a DC voltage of 10 millivolts is applied at t equals to 0. Right? So here, our input is a constant. Right? So this is pretty straightforward. This is our governing equation. So we know that the op-amp is initially sitting at 0 volts. So we don't have to include an integration constant. And we know that the product of R and C is 25,000 times 10 times 10 to the minus 6. And then our VI is just equal to 10 millivolts. So we're just integrating a constant. So this is just the area under a rectangle. The width of that rectangle is T, and the height is 10 millivolts. So in other words, 10T, it's the integral of 10T evaluated between T and 0. And when you simplify the fraction here, you get an output voltage of negative 40T millivolts. So notice that this output voltage is linear with time because the area under a rectangle is linearly related to the width of that rectangle T. So this is another case where the op-amp would saturate unless you turned off the DC voltage at some point. I think you'll observe saturation in one of the labs, actually. All right, 2 more slides, and I set you free. Differentiator is the exact opposite, right? You put the capacitor on the input path, and you put a resistor on the feedback. Let's do the same exercise as before. IC has to equal to IR. So the value of IC, right, because node A is once again sitting at 0 volts. Right, so the current here, IC is equal to C times the derivative of VI. And the current here is equal to 0 minus V naught divided by R. Right? So IR is equal to negative V naught over R, and IC is equal to C times VI prime. Set those two equal to each other, and you rearrange, and you get this very nice expression, which is that V naught is equal to negative RC. So again, we have this constant of R times C multiplied by the derivative of the input voltage. And so as the name suggests, our output is proportional to the derivative of the input. Now, this is not often used, and the reason for that is noise is often high frequency. So if you've heard of the term white noise, if you actually look at what a white noise trace looks like, it just looks like squiggles going up and down really fast. And so squiggles going up and down really fast would be a problem for this, because the derivative of those squiggles is very large, right? If you're just going up and down really fast, you have very large derivatives. And those large derivatives are noise, and they introduce noise into your output. And so unless your input is really clean, this would not be a very good circuit to implement a differentiator. All right, I think we have one more slide. Okay, so we have an example of a differentiator with a 0.2 microfarad capacitor on the input and a 5 kilo ohm resistor on the feedback. And we are asked to sketch the output voltage V naught given this input. So we have this triangular waveform for V of I. So VI here is given by this input voltage. And we are asking you to compute V naught. So first of all, before we do the math, what is the shape of V naught going to be here?
It's gonna be a step graph.
Yeah, that's very good. Step is very, yeah, square wave isn't that? Those are both right. They're square waves. And is the square wave gonna go from positive to 0, or is it gonna go from positive to negative? Positive to negative, excellent, right? Because the derivative here is positive, the derivative here is negative. So it's going to be positive constant, negative constant, positive constant, negative constant. And so if we actually, first of all, we have to figure out what the time constant is, which is equal to 10 to the minus 3 seconds, right? Because that's the product of the R and the C. And then we have to multiply that by the derivative of this waveform. Go ahead, Sebastian, no worries. Right, and so the derivative of this portion is equal to 2, right? For a rise of 4 and a run of 2. Did I go over time, by the way? No, right? Okay, good. And the derivative of this portion is negative 2, and the y-intercept is 8. Right? So these terms here, we have to take the derivative. So derivative, this is 2, and derivative, this is minus 2. And so that has to get multiplied by this RC constant and the minus sign. And what you end up with is a square wave. And actually, what I said it was going to be positive, negative, positive, negative. It's actually the other way around because of the negative sign here. So it actually goes negative, positive, negative, positive. And this value here is 2 millivolts. And it's 2 millivolts because you're multiplying 0.001 by 2000. By, sorry, 2. This is units of volts per millisecond. So let me see if I get this right. So you have 0.001 that's multiplying this. So I should, never mind. Yeah, so you have a 0.001, and this gets confusing with the units here. So basically the slope of this, because it's not really specified here whether this is in volts or millivolts, but I think it's implied that, yeah, it's implied that it's in millivolts. So the vertical axis here is millivolts. So we have a rise of 4 millivolts and a run of 2 milliseconds. So the voltage here is 2 volts per second. When you differentiate that and you multiply by 1/1000th of a second, you get an output voltage of negative 2 millivolts for these sections, and you get a voltage of 2 millivolts for these sections. The square wave as predicted. Okay, we are done 60% of the course. That is a good thing. And we haven't even hit the spring break. So if you haven't given your shipping address to the TAs, please do that immediately. If you haven't, or if you're not getting it the lab kits shipped to you, make sure you schedule time to pick up. What else? Midterm is on April 12th. Great, happy to hear it. Homework 3 is the due date for homework 3 I've extended to April 7th. Do the homework, it's good practice. Do as many questions from the back of the book, it's good practice. And I will see everyone back here after the break. Stay safe.